Okay, today I thought we'd return to the Kepler orbit and think a little bit about one extra symmetry that the inverse square law possesses that doesn't really correspond to other choices for central potential. And there's a lot of real deep mathematics that falls into this. It's also, in a way, the heart of why the hydrogen atom, which is sort of a different law, although it's also an inverse square law, even in quantum mechanics, has more degeneracy in its energy levels, etc. There's a lot more symmetry in the Coulomb potential, or the inverse square law, the Kepler problem, than you might initially think. And part of this is, well, the symmetry involved, of course, is geometric in nature, but it lets us connect together a few of these different conserved quantities. We've seen a number of them already. We know that energy is a conserved quantity. Okay, that's one scalar conserved quantity. The angular momentum is a conserved quantity. That's a vector conserved quantity. And there's this extra conserved quantity, a very weird one that doesn't really seem to play much role, and yet it's there, and we should account for it. And this is the Laplace-Runge-Lenz Vector. So I'll call it the RLR vector for short. But it's another vector that comes out of these different orbits. I'm going to do this for an ellipse, but it's true in general. And we'll kind of see where it comes from in a very general setting. Okay, so we're going to start this pretty generally. I'm going to start by writing down Newton's second law. But I'm going to write it in a trickier form. Okay, that is actually Newton's law. The net force that's acting on an object is the rate of change of its momentum. That's the way Newton actually first wrote his second law. And it'll be a little more useful to us here instead of writing it as ma. Now, the net force in this case is just the gravitational force. And we've already gone through the whole process of reducing the two-body problem to a single effective one-body problem. So I already know what this force is going to be. And it's going to be, well, I don't want to nail myself down with having to have a inverse square law. I'm going to just write it as a generic central force, F of R, R hat. Okay, so that's a generic central force, depends only on R, and it points in the sort of radial direction. That's not so bad. And what I want to do now is I want to, first off, take the cross product of both sides of this equation with the angular momentum vector. It sounds like a really weird thing to do, but you'll see why this is useful in a second. So over here, I'm going to write this one first. I'll write P dot cross L. And on the right-hand side, I'm going to rewrite R hat as vector R over scalar R. And of course, I'm crossing that side with L also. The next thing I want to do is recognize that L, the angular momentum, can be written in terms of a cross product itself. Let's recall that over here. We usually write this orbital angular momentum as R cross P. And actually, let's do that. I don't even need to read the mu yet. So I'll write this as R cross P. When we plug that into the cross product over here, I'm going to have to use a vector triple product, meaning a cross product with another cross product. And there's a very nice relation that lets us simplify that. So let me start by writing that out a little bit. Okay. This triple product here can be simplified using the back minus cab rule. It's pretty common in physics. It's probably a different name for it in math, but I'll write it down. If I want to do say vector A cross vector B cross vector C. So it's this triple product. Please notice this is not associative, so you do have to put the parentheses in the right place. We get something that is the back minus cab rule. So it's B times the dot product of A and C minus C times the dot product of A and B. Back minus cab. I don't know of a very convenient way of remembering this other than back minus cab, because it's very easy to accidentally say, oh, is it B dot A times C? No, just remember the first letters are the vectors and the second two are the dot products. So in our particular case, I want to do that using this P. So following down, now I'm going to apply my back minus cab rule. The middle term is this R, and then I'll have a R dot P. And then my last term is p, and I'll have an r dot r. Well, that's just r squared, the scalar quantity, r squared, so that's not so bad. Next, what I want to do is rewrite p. We know that p, adding to my list over here, is mu times r dot. That's sort of the definition of the momentum. It's mv here. M, of course, being the reduced mass of the system. We've already contracted this down to a one-body problem. And then what I want to do is, on the right-hand side, I'll replace these two p's with this. On the left-hand side, I'm actually going to use the fact that L is conserved. So L dot, meaning the derivative of the angular momentum vector, is 0. Well, 0 vector. So that means if I wanted to, I could take this time derivative off of the p and put it just on the whole product altogether. Because if I tried to expand that out using the product rule, the part that has a derivative of L would actually just give me a 0 anyway. So let's write that. So there's my left-hand side. On the right-hand side, I'll factor out a mu and rewrite some r dots. Okay, so far, not so bad. Let's see if we can do one last little bit of simplification. I see a total time derivative on the left. Maybe we can find a way to write this as a total time derivative, or something involving a total time derivative on the right. Okay, so over here on the right, let's see what we can do. First off, I'm going to flip these two terms by pulling out a minus sign. I'm also going to put this r inside, but also pull out an r squared. I know that was a lot to say. The reason for this is I'm already kind of anticipating this f of r being a 1 over r squared, which in the front here, that'll be a constant. That'll be pretty nice. But let's go ahead and factor out an r squared and see what we're left with. Okay, so I pulled this out. This r squared was pulled out. The 1 over r has to go inside now for that term. This term, so I pulled out a 1 over r squared, which means I got to put that 1 over r squared back. Now we can also use the fact here, I'll put it sort of in another bit of green if we have room down here, just barely, that if I look at r vector dot r dot vector, this is the same thing as half the time derivative of r dot itself. And you can kind of see why that is, right? If I try to apply the product rule to this, I'll get an r dot dot r plus an r dot r dot. Well, those are the same terms, commutative between those dot products. So the 1/2 kind of cancels that out. But what is r dot r? Well, that's r squared, the scalar. But now I can just take the time derivative of this scalar quantity, and I'll get a 2 coming down, canceling that 1/2. And I'll just have r and then times the chain rule r dot. So somewhat conveniently, this dot product of two vectors ends up being just the product of their individual magnitudes. So it's kind of nice that that turns out in this particular case. These could be kind of arbitrary directions, and it simplifies pretty nicely into this r times r dot scalar. So now, using this relation right here, and recognizing that I have an r vector times r dot, and then remembering I have pulled in an r, but I've pulled out an r squared, when all is said and done, we'll have. Okay, now again, it doesn't look like we've done much here. It's maybe a little simpler, no more dot products involved. But it turns out that this combo in square brackets is actually very nice. It is exactly the time derivative of the unit vector r. Okay, so let's clean this up. I'll bring stuff to the top, and we'll see that in action. Okay, so here we are. This is the last line of the previous board, and now I'm rewriting this as the time derivative of just r hat, basically. Well, I wrote it as r vector over r. And if you don't believe me, go ahead, apply the quotient rule to this, and you'll see what happens. So it's, bottom times the derivative of the top. Well, that would be r times this r dot. Remember, we're going to have a 1 over bottom squared, so that r will cancel one of the r's in the r squared denominator. And then minus the top, there's my r, minus times the derivative of the bottom, which is the r dot, again, all over r squared. So this comes out pretty nicely. All right, we're almost done. Now look at what we have. A total time derivative on the left and something times a total time derivative on the right. Now, as it is, that's not very useful. But in the special case where f is a inverse square law, we see something pretty nice. So in fact, we're usually taking the case of f being something like gmm over r squared. I'm going to leave that in my sort of generic notation as kappa, where that's just sort of the numerator, because this could hold for Coulomb's law also. The 1 over r squared in f and the positive r squared power here cancel. And that's why this is now so nice, because the prefactor to this total derivative is a constant. So let's pull everything over onto one side. And look at that. We have the time derivative of this admittedly kind of messy thing in parentheses is 0. Well, I'm going to call this combination a new vector. It's usually given the letter capital A, and that is exactly this Laplace-Runge-Lenz vector. It is a conserved vector. So ddt of A is 0, just like ddt of L was 0. So it's another conserved vector quantity. If you want to think about what direction it points, well, it's a little hard to see immediately. I can see that this second piece points in the r hat direction. What direction does P cross L point? Well, if I imagine some generic point on my ellipse, or any conic section we have here, P is going to be tangent to it, and then L is, at least the way I've drawn it, out of the board. It'll either be into the board or out of the board once we've chosen our plane. And if we use our right-hand rule, if I have P cross, say, L, P cross, boy, this is, okay, P cross L is, I don't want to be giving you the middle finger here, but it's giving you a direction that's kind of up. Now, the thing is, R itself points along this direction. When I add that to this, at least at this point, upwards direction, weighted by the appropriate constants, and that's actually a little irritating to have to work it out, it turns out that the Laplace-Runge-Lenz vector actually does point to the periapsis from the CM. In other words, it'll point kind of along the long axis of the ellipse, if it's an elliptical orbit. A better way of seeing that without involving a bunch of hand-wavy geometry is to look at it analytically. So here we have our A. Let's just assume for a sec that A points along the x-axis. I haven't specified anything about the orbit at this point. Let's just say, I don't care what direction my orbits point. Let's just pick A to be along the x-axis in polar coordinates. And I want to compute A dot R. Now, first off, since we've lined this up along the x-axis, I know I can write this as AR cosine phi, where phi is my usual polar angle. That's just the definition of a dot product. But if I go up to my expression for A and I dot it with R, what do we get? Well, I'm going to get this dot product minus, well, R dot R, of course, is R squared, and 1 over R, that extra 1 over R will cancel. So we end up with this minus mu kappa R. This thing right here is a scalar triple product. I have a cross product dotted with another vector. And one nice thing about the scalar triple product is it is equal under permutations, cyclic permutation. So what I can do here is I can replace this with something like, well, we have to keep the cyclicality correct. So if I say move the L to the end as the dot product, and then the P moves to where the L was, and the R comes to the front in the cross product, that's totally valid as well. And this thing right here is L. That's the angular momentum, right? That is the definition of the angular momentum we had over here. So this is L dot L, which is L squared. Okay, that's kind of nice. Now I can use this to go solve for r. Look at how I have an r showing up on both sides of this equation, so I can move stuff around and factor. Okay, so we'll have a cosine phi plus mu kappa all times r equals L squared. And now let me go ahead and take this equation, bring it up to the top, solving for r, since we're at the bottom here. And I'm also going to divide everything out by mu kappa to write it in a very suggestive form. Okay, so here we are. This is our new RLR vector, and we've been able to rewrite, using a dot product of r with that, r, the distance, if you will, in a very suggestive form. This should look pretty familiar. This is the equation of a conic section in polar coordinates, the orbital equation. We have the orbital equation, and we already know by comparing it to previous results that the thing in the numerator is the semilattice rectum. Of course, we knew that already. But also, we get the eccentricity for free as well. And notice it's a over mu kappa. So we have this very nice expression that relates the eccentricity to the magnitude of this unusual vector. Now, we might be a little careful here, because if we do a little bit of counting, it might seem like we've got too many conserved quantities. Let's take a look. First off, in our reduced problem, where we only have a single body effective potential, we have a phase space that's 6-dimensional. In other words, my reduced mass particle here can occupy 3 directions in space. Okay, I know this is in a plane. Yes, we'll get to that. But in general, there are 3 spatial dimensions that can be occupied. And of course, there's the 3 degrees of freedom for the velocity vector. That's 6. We also, of course, have the single extra dimension of time, which parameterizes where we are on a particular orbit. So we have these 6-dimensional space with time, but if we count up how many things are supposed to be conserved here, seems like we need some constraints between them. Energy is conserved, that's 1 scalar. Angular momentum is conserved, that's 3 components of a vector. And we just said that this vector, A, is also conserved. That's 3 more components. So that is 7. That is 7 total components that we need to have be conserved. But again, counting, 6-dimensional phase space, time is 1 free parameter, so there should be 5 dimensions that are covered. We should only have 5 conserved quantities. I just talked about 7. So what gives? There should be at least 2 relations between these conserved quantities. And there are. One of them is that A dot L is 0. And we can see that pretty regularly just right from here. I know that if I dot this cross product with L, I'll get a 0 because of the cyclical nature of that triple product. And then R dot L is also 0 because we've chosen L to, well, not just chosen, L is perpendicular to the plane of motion of this ellipse. R lies in that plane, so that has to be true. The second relation is a little more annoying to write down. And it's related to the magnitude of this vector. So you can go ahead and square this, dot it with itself. I'm bringing in the eccentricity a little bit too. Or actually, maybe an easier way is just to go back to recognizing that A over mu kappa is epsilon, and we already had an expression for the eccentricity in terms of the energy and L. So move some stuff around, square both sides, and you'll get this relationship between A, E, and the magnitude of L. So there's 2 extra conditions that reduce the 7 conserved quantities down to really only 5 independent ones. Okay, so what we have here now is this new vector, the RLR vector that we derived starting from a very general force law, but then crucially using the fact that this was an inverse square force law to get something that was conserved in time. It has some nice analytical properties. Geometrically, it's, I guess, the direction of the periapsis of the ellipse, so that's kind of why these ellipses don't precess, because that would mean that A is changing with time, so these ellipses stay fixed, assuming there's no perturbations beyond the inverse square law. And you might ask, well, can you get other conserved quantities by using different force laws? The answer is kinda. It depends. For example, in the case of a harmonic oscillator, where this force is a linear force in R, you do get a conserved quantity, but it's a conserved tensor quantity, like a matrix quantity. So we don't get a conserved vector like we do here. And generally, the orbits are going to be a lot more complicated. They don't close on themselves nicely the way that these conic sections do from the inverse square law. And that's really, again, tied to the fact that this A stays fixed in location, so you don't get wobbling or gradual tilting unless you include some perturbations. At any rate, hopefully that's a nice little intro to this particular vector and why there's an extra little bit of symmetry in the inverse square law that we don't see in other central forces. And at some point in the future, maybe we'll see how this manifests in, say, a quantum mechanical sense. QED.